Just a second. Well, good morning, everyone. I hope it's a good morning for you. Thanks for having me here, and special thanks goes to the LECO team for the last night. And now to the topic. Let's see. Where should I point it? Down, just down. I see. Okay, sorry for that. So, I hope you also like rap music, because I'm gonna rap through this presentation very quickly. It's a lot of information and a limited amount of time. Yeah, sit back, relax, and try to enjoy. Air pollution is responsible for around 9 million premature deaths every year. And it possesses a bigger life expectancy threat that, for example, smoking, diseases, and even wars or other armed conflicts. In fact, WHO says that 99% of people in their ambient environments breathe polluted air. I don't know where that last 1% is, probably on a mission to Mars, so no air pollution, obviously. And then, even before COVID, European citizens spent most of their day indoors, being in contact with the indoor environment of their homes, offices, whatsoever. And there is, in Europe, only 100,000 chemicals registered in use, which surrounds us in our environments. And many of them possess or can potentially possess health hazards. So that's why we have this Inquire project. So in this project, we analyze air, dust, and human samples, and trying to connect all this with diseases like asthma, allergies, and so on, especially in small children. Why dust? Because dust is a good proxy for air quality, as it absorbs a lot of chemicals. And there was this big study published just last month, I think, led by my boss, Peter Haglund. First big collaborative trial on dust, in the European dust. So we're kind of doing similar thing, continuing and expanding that. So the idea is, sampling these 8 countries for the dust, we're gonna get like 250 samples. But it's not the topic today, because as in every big project, everything got delayed. So I just got samples a couple of months back. So in the meantime, I was playing with like some trial samples. And that's what I'm gonna present more or less, and the workflow. So the aim is development of this workflow, first of all, for cleanup, extraction, cleanup, and possible fractionation. Then data processing, that's the most interesting part to me. And then identification of chemicals, classification, and quantification, semi-quantification. I asked my parents, my friends, to collect some samples. So you see the places: Lviv, Ukraine, Munich, Germany, and I collected dust from my apartment in Umeå. And then we had this sample from collaborative trial and NIST Standard Reference Material as kind of US sample, and blanks. And then for software alignment testing, I spiked those 4 samples with 4 different concentrations of different standards in total 152 compounds. So the workflow: first of all, you have dust, you have to extract it, but first of all, you have to sieve it. And that's very kind of time-consuming and ugly thing to do. I don't know if you've ever seen the dust sample, but it's gross. And I was like, my eyes, my eyes. Yeah. Then you extract it. We decided to go for fractionation. I used this nice Buchy-Synchro Plus analyst instrument. The thing is, it allows you, it's kind of 2-in-1 SPE thing, and then evaporator. So you just switch the valve and you evaporate. You don't have to transfer anything anywhere and so on. Very convenient one. And then GC GC-TOFMS with LECO Pegasus BT 4D. And peak picking and library search was done also in Chromatov, LECO Chromatov. That's what my apartment looks like. 2 fractions, and that's 3D. So the huge peaks in the first fractions are what? What do you think? Any guesses? Phthalates. I have this very nice, what I call it, phthalate-based flooring. So these huge peaks are phthalates. And the second one, the big peaks, these are DIMLA compounds. They are used in all those disinfectants and so on. During COVID, their use increased a lot in the post-COVID times. Yeah. So the next thing was classification of junk, column bleed, and so on. This I did with spectral filters and chromatographic regions in Chromatov, and it looks like this, like Jackson Pollock's work. But it works pretty well. It takes some time to create all these regions, but it helps to like get rid of around 70% of features per sample, which is a lot. Then I did some data conversion and cleanup using my custom Python script, and then my favorite part, intersample data alignment. So in the end, I want to have this big table with like areas or concentration per sample for all the compounds and the information about the compounds, like Cas number, inch key, whatsoever. So that's how I imagined it in pseudocode. And then there are many algorithms for spectra similarity comparisons and so on. So I tested a lot of different open source and vendor software. I provide only 10 here, but none of those gave the result I wanted. Only this one, GNU, but it's kind of from 2010 or 2011, a bit obsolete, but it was doing the job, like, in a way. But it was also a black box to me, so after all, we decided to write up something by ourselves with the help of Saer and Denise from University of Amsterdam, especially Denise because she was the one who was writing the code. So I call it for now Julia Aligns to DGC. Sorry, I need to. Julia is a language, programming language. That's a good gene. All right, so we wrote this script for intersample data alignment for 2DGC data. And then as I told you, I spiked this 152 compounds, was able to detect 146 because some of them are eluting too early or have other problems with GCMS. And then I looked what GNU was able to pick up automatically and align. So that's what you see here. As can be seen in the 0.05 picogram sample, only 10% were found in blank, so that means that only 14 compounds at this level are detectable. In other samples, they have those compounds already in the sample because these are mostly like terpenes and stuff like that. And then I did the same with Julia script, and as can be seen, the results are pretty similar. Then I did some manual review, data curation, and was able to kind of got a bit more compounds, but not that much. But the conclusion here is that the script works pretty well. Of course, it will be improved. I don't speak Julia, unfortunately, and Denise is out of academia. So now I kind of hopefully improving it using ChatGPT. My friend Jack Daniels and magical swear words, but seems to be working. And what the script does, you can see here. So it takes LECO Chromatov result file, converts it to CSV, then removes all those things from the classifications that were classified as bleed toluene or other solvent whatsoever. Then also I added some name or name plus mass filters. I will show it in the next slide. Then I also clean up the spectrum a bit, removing zero intensity masses or low intensity masses. And then, of course, it does the alignment using DISCO algorithm. I also tried normalized dot product algorithm. It can be like replaced with any you wish. And then it also merges things post-alignment, after the alignment, and does the feature I really like here, the library search. It's good for the review, and finally visualization of library search results. So the result table looks something like this, and then that's the name plus mass filter. So you can see the top compound is basically toluene, but since RI value was out of tolerance, it was assigned. It was named this one, bromobenzoyl, blah, 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 blah. But then using this name, MZ filter, I kind of simply say the script that if you have this name but don't have 1 of 7, it's toluene deleted. As simple as that. And then that's the library match result table. And yeah, this is just the illustration of the graph. So for the compounds with a good spectra and good match, you see it's the same basically. It looks very nice. Then it also helps for with the review of the data, because this compound was unknown after Chromatov search, but it was matched as parylene by this script. All right, then, yeah, in the script, as I said, there's this blank bleed filtration and prioritization. Also, I want to add, for now, I have Python script, but I'm going to translate it to Julia and incorporate it in this script to have this classification, functional use classification, and also chemical classification. And then identification, still working on it. And finally, quantification and this prioritization of a list of compounds to be submitted to our toxicological partners to check for potential health hazard. And now to some results. 3 cities. And first of all, the classes detected. So I was able, after all these filtrations and so on, still to have like 3,000 components, compound features. Half of them are still trash, I guess, and will be removed in the further steps. But you can see the main classes. Phthalates, terephthalates are big, and also a lot of PCPs and other things. This is a similar graph from this paper I mentioned. They have pretty similar results. They have like 650 confirmed GC GC-TOFMS compounds. And I would expect in our samples the same in the end, maybe a bit more. But yeah, we'll see. And then I decided to feed all this data to PCA, and the software was like, yo, man, you sure you want to do that? It's going to be crap. And I was like, I consider it a rhetorical question. Do I have a choice? No. So that's what it looks like for 5 samples. And if we clean up a bit and look at a couple of classes, PCPs, pesticides, and UV screens, you see this separation pretty well. So in the US, 1 types of these compounds are used, in Europe different, and then you have this separation between like Munich and the composite European sample. Then Umeå is up in the north, so different compounds, and Lviv is Ukraine, non-EU country, so also a bit different regulations and so on. And basically, that's it for now. I didn't have time to look into any levels concentrations because I was compiling data just on Monday. When I submit abstracts, I think it's true for many of us here. It's rather a wishful thinking. So it's like, oh, I have half a year. I will rule the world in half a year. So. But yeah, then it's the first day of the conference and you're still sitting compiling data. Fast, highly automated data processing workflow was kind of sketched and will be developed further. GC GC-TOFMS analysis reveals presence of really high amount of different chemicals and higher number of chemicals than the previous GC-TOFMS analysis. And the European dust contains enormous number of various compounds. As for the future work, I'm gonna identify the compounds and prioritize them, as I said, and quantify them or semi-quantify them. With this, I would like to thank, first of all, my boss, Peter Haglund, then guys who helped with the script, especially Denise, all the partners, all the people who gave money, and all of you for your attention. And last but not least, I'm looking for a job. So if you're looking for me, just text me. Thank you very much.